All right, with lipids, to be honest, I normally don't teach this chapter just because, like this year, we run out of time. But those of you that are going on into biochemistry will see this over and over and over again, so I feel like I wouldn't be doing this course due justice without showing it to you guys. So let's do a brief crash course on lipid chemistry here. Lipids can be broken down into two different groups. The first one is made up of complex lipids. And I don't really like the term complex lipids, but it's what the book uses. And these are lipids that can be hydrolyzed. So we could saponify all of these lipids if we wanted to, which means you react them with sodium hydroxide. These are different than simple lipids, which oftentimes aren't simple, but they cannot be hydrolyzed. All right, so let's break these apart. Most of the lipids we've seen so far fall into the complex lipids class, which means they will react with sodium hydroxide. The first class is made up of waxes. Oh, shoot. Next class is made up of triglycerides. And the next one is made up of phospholipids. All of these can be hydrolyzed. So if we look at what a wax is, I'm just going to really briefly write out what a wax is. It's basically an ester where both R groups equal long alkyl chains. So it's just a simple, really aliphatic ester. Triglycerides are what we saw in class with in lab with our nutmeg soap. Where again, these R groups are long aliphatic chains, and then you've got the main glycerol backbone. Phospholipids are really similar to triglycerides, but with one major structural feature. So you've got, yeah, exactly. You've got these R groups coming off, but now you've got a phosphate backbone coming off of it. And these are seen oftentimes in cell bilayers, so you guys have most likely seen this in biology already, but this is still an example of a fat. All right, now let's look at simple lipids. First one is made up of steroids. Then we've got prostaglandins. We'll go over these. So I'm just going to show you guys simple structures for these. And then the last one is terpenes. So steroids have this general structure of a bunch of bicyclic ring systems, or polycyclic rings. Oop. So it's got these 6-membered rings fused together in this orientation, and then on the end there's a 5-membered ring coming off. I'm not going to show all of the substituents coming off, but it's always going to be this 4-membered fused ring system. Prostaglandins, I'm not even going to try drawing all of these structures right now, but I'll list some of their features. The first one is that they have 20 carbon atoms. They have a 5-membered ring. And then the last feature for prostaglandins is that they have 2 side chains. there's a whole variety of prostaglandins. They're used in biological signaling very regularly, and they're very structurally diverse, so I'm not going to draw an example one. The last one are terpenes. And terpenes have this structural unit in them. Where they all have isoprene units that repeat in them, or they've got multiple isoprene units in them. All right, so now crash course. You guys ready?
Let's do it.
Let's do it. All right. Wax. So let's take a look at this wax. Ooh. This is spermaceti wax. It's the wax that's isolated from the heads of sperm whales. So if you guys have read Moby Dick or any of those classic whaling books, they're always hunting sperm whales. The reason behind this is that sperm whales have this large store of fats right in their head, and they think that this fat is used to help them stay buoyant, and they think it's used for a type of echolocation or sonar so that they can figure out where they're at.
So why do we want it so bad?
Yeah, that's a good question. It was used as a wax for candles and as a fuel. So what they would do is they go harvest these sperm whales. An adult sperm whale, surprisingly, has 500 gallons of spermaceti wax in it. So they would send out these whaling ships. I mean, on a given day, they might catch one or two of these, and then they would store these barrels of wax, process it on the ship. That way it wouldn't go rancid. And then they would take it inland and then use it for all of these applications. The problem was, obviously, we started hunting whales to extinction, and we got a little overzealous with this wax. So waxes today are mostly synthetic waxes. We don't tend to harvest them that often from whales, at least. Does anybody know another major wax that might be similar? Beeswax. So we make candles out of beeswax. That's the other animal source we use primarily for waxes.
So did they just not know how to make it synthetically?
No, now we can make this
I mean,
synthetically.
before,
Yeah, before we did
that's
not
what
have the technology to. Yeah, whaling continued all the way through like the 1930s before we kind of got the picture that this was a bad idea.
I don't know if this is a new method, but my friend was telling me you can make wax out of like coconut too now.
Make it synthetically?
Yeah, or coconut oil wax. And it's better for like, something about you said it burns.
Yeah, I'm not sure. I'd have to look into that. All right, and the other nice thing with waxes that they used them for was that they are very hydrophobic. So those long alkyl chains make this a nice water repellent, so you can actually put wax coatings onto things and make them waterproof. So that was another common use for waxes. All right, let's go to triglycerides. Work our way through this. So triglycerides, like we saw in lab, always have this major structure where you've got a glycerol unit on one end, and you can form ester linkages to a bunch of fatty acids. These fatty acids can vary in their identity and size, and that changes the overall property of the oil. So let's take a look at some common fatty acids. And this is from your book. Sorry, I've got something in my throat. The first one is lauric acid. This is very, very commonly found in soaps. So have you guys heard of sodium lauryl sulfate in shampoos? That's a derivative of lauric acid. You've got mysteric acid, palmitic acid, stearic acid. I'm not even sure how to pronounce the next one. But you can tell as you go down the chain, the melting point increases just simply because you've got more dispersion forces going on, right? So the longer that aliphatic chain is, the more dispersion forces can play a role in increasing the boiling point and melting point. Conversely, if you look down at the next one, we've got a cis alkene in there, and all of a sudden the melting points drop to 0. So all of these up here can pack tightly, which increases their boiling point. But if we go down to our unsaturated fats, which are shown here, these cannot pack tightly. And therefore, their melting points are much, much lower. This is why we consider unsaturated fats as liquids and saturated fats as solids, right? That has to do with the cis-alkene. What's the problem with the transalkene? Yeah, we can make it synthetically on accident, but our body's not used to processing it, so we're trying to remove it from foods a fair amount. Oh, thank you. All right, so let's take a look at some fatty acid contents for these. So if we look at beef fat, these are, let's go up to oleic and linoleic acid first. So oleic right here is a unsaturated fat, and linoleic is another one. So if we look at beef fat, it's got 55% saturated fatty acids. The rest is unsaturated fatty acids. You can see milk fat, lard, and human fat, kind of same compositions. These are the solid fats that we encounter on a day-to-day basis. Versus our vegetable oils, they've got a lot of saturated fats and a lot less unsaturated fats. So you can use this to kind of see the rough distribution of the fatty acid side chains on each of
They
these.
have less saturated than the animal fat.
Yep.
I thought you said, oh, okay.
So animal fat has a very high percentage of saturated fatty acids. Vegetable oils have a very low percent of saturated fatty acids.
You want saturated fats, right?
Yeah.
It's unsaturated that's bad, right?
You want it in moderation.
No, unsaturated fats conventionally are better for you. But, I mean, take everything with a grain of salt. You do need a balanced diet in general, though, right? You don't want to chug olive oil every day.
Unsaturated, good.
Saturated is typically considered bad. But there are a lot of people that say, well, coconut oil and coconut fats are actually not that bad for you, and they've got a lot of saturated fats. Yeah. So it's not a cut and dry, one's good, one's bad. All right. The cool thing with fats, or I guess uncool thing with fats, depending on your relationship with them, is they are great at storing energy.
Which one's solid temperature?
Saturated fats. Because they're linear without the kinks in them, they pack really tightly and they're solid. So they're great at storing energy. They have 9 kcals per gram. Oop. This is way better for storing energy than carbohydrates or proteins, right? So if we look at carbs, we've got 4 kcals per gram. And proteins. This is also why it's hard to get rid of fat. So if you're overweight, it takes a large amount of energy to burn off fat. It's the main biological way we store energy, especially during times of surplus energy, right?
So then why is it that for sporting games, like it was like protein shakes and pasta rather than just giving us a piece of steak?
That's an interesting question. So if you're thinking about what's most readily available, your body has a sequence of energy stores that it goes after. Simple carbohydrates, number one easiest thing to metabolize. Second most is going to be complex carbohydrates, so things like starches and pasta. And then it'll go down the chain to fats. So fats have way more energy, but they're not as easily metabolized. And then if you're absolutely out of all of those, you'll start digesting protein, and that's considered wasting.
So you're saying like if you're gonna use that excess, then you should have the steak for dinner the night before, and then have like protein or something.
I mean, most athletes would say you want to have a large amount of simple carbohydrates immediately before your race and have a reserve of complex carbohydrates in your system afterwards. Burning fat isn't the go-to source of energy for athletes, simply because they don't have a lot of fat to begin with. Yeah. All right, so let's cover the reactions. I'm not going to show you guys these reactions because you've seen them before. So hydrogenation of unsaturated fats. We've already covered hydrogenation, but if you've got an unsaturated fat, you can hydrogenate it back to an alkane, right? The second one we saw was saponification.
Oh, yeah. We know that.
Or acid catalyzed hydrolysis.
That's what I'm saying.
Okay, so it's
No, you're being serious. We just made it.
So we can convert from our triglyceride back to either a carboxylate salt or back to our fatty acid. So that's just simple ester chemistry. The next one we can do is one I haven't really talked about, but is very important. If we think about triglycerides, they're just fancy esters, right? And we can transesterify any ester and change out the ester group, right? So in this case, we can take glycerol and we can swap it out for a different alcohol group. And the reason this is important is we can convert it into new molecules that look like this. So methyl esters and ethyl esters. What are these used for? You could think of cars. What might you put in a car? Diesel, right? So this is considered biodiesel. The R chain is probably going to be much, much longer. But by transesterifying your triglycerides, you can actually convert it into a fuel source. You can't burn regular triglycerides very easily. So biodiesel is a big booming industry right now. The last one that we didn't cover is autooxidation. And that's when it becomes rancid. So I'm not sure if you guys have dealt with rancid fats, but rancid fats smell really, really awful. And the reason behind this is that you have a reaction with radical O2 plus fat equals something that's very, very smelly. I'm not going to go into the reaction here, but if you are interested in reading about it, it's in section 11.2, and it has a lot to do with radical chemistry. Oxygen as a gas has a lot of radical character, so it will actually react with double bonds in the same way as other radicals. All right, I think that's... Actually, we've got a few more. So the last thing I wanted to talk about with triglycerides is soap. So this is our classic soap molecule, right? And we said in lab that soap works well because you've got a hydrophilic head and a hydrophobic tail, and you can wrap up these oil particles in micelles. One thing they don't talk about very often... 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. This molecule is also considered a soap because, again, it's got a hydrophilic head and a hydrophobic tail. And this is sodium lauryl sulfate. Why would we add sodium lauryl sulfate to soaps?
Make it bubbly?
Yeah, it makes things bubbly. What's one thing you noticed too when you reacted calcium chloride with your regular soap?
Calcium chloride.
Yeah, in lab. Soap scum, right? So regular soap will form soap scum. This one will not form soap scum. So it drives me nuts in these natural food stores where they say, our soap is chemical free. And then I just go, are you kidding me? Like, everything is made of chemicals. I don't know how people cannot see that. And then they say, well, it's sodium lauryl sulfate free. And it's like, all right, but then it forms soap scum. It's not that chemicals are bad or good or whatnot. There are some great chemicals and there are some bad chemicals. Just don't throw out chemical free on a packaging and expect people to buy that. But apparently people do, so they continue to do that. Anyways, yeah, sodium lauryl sulfate is, there are some people that have allergies to it, and if you do have an allergy, you do have to buy soap that does not have sodium lauryl sulfate. All right, so let's continue on to phospholipids. So with phospholipids, what we have is the hydrophilic head. And then we've got this hydrophobic tail. Our body makes use of these for cell membranes. So if you look at how membranes can be structured, you could have three different types of membranes. You could have a fatty acid membrane with simple waxes, with simple fatty acids, or you can have a phospholipid bilayer.
This is for what?
This is how cells are normally made. This is phospholipids. And then if you do triglycerides, you can see triglycerides actually don't pack as well as phospholipids, so it's actually good that we only have two fatty acid substituents. They pack much more tightly and will hold the cell together. If we had fatty acids or triglycerides, our cells would likely be damaged if anything ran into them. So let's take a look at our normal cell bilayer. You've got the two parts. You've got your phospholipid head. At each end, and then you've got, actually let me move this over. I'm going to change colors. And then you've got your fatty tails. And so you may notice that I've shown this diagram of a phospholipid bilayer, but there's more going on than just the phospholipids, right? What's stuck in between them? Yeah, steroids. What's the main steroid within a cell membrane? Cholesterol, right? So we can say cholesterol is embedded in cell membranes. Why is it important that we have cholesterol in our cell membranes? Yeah, so we want to regulate how fluid or non-fluid, for that matter, our cells are. So we can add and remove cholesterol into phospholipid bilayers in order to change the property of the cell membranes. We get a lot of it from dietary sources, but we can also produce it too. Yeah. All right, so that leads us into our next section where we talk about steroids, one of which is cholesterol. So steroid numbering systems are a complete nightmare. If you look at the numbering system here, you always start at this 1, and then you go all the way around the ring, and then you cut over from 8 and 9 into rings C and D, and then the rings themselves are numbered. So you've got ring A, B, C, and D.
But it went from 9, 10, and then up to 11.
Yeah, why does it do that?
Yeah, that's why I said cholesterol numbering systems are screwy. This has more to do with fused ring system numberings. And we didn't get into that, but if you go on and you take advanced organic chemistry, you may cover numbering at bigger and bigger ring systems. So the example that we have is cholesterol. And we said that cholesterol embeds in cell membranes. And this is an interesting debate in popular culture, is whether or not cholesterol is good or bad. And we've got two different types of cholesterol. We've got HDL and LDL. The first one is high density lipoproteins. LDLs are low density lipoproteins. Has anybody taken the nutrition class here? Nobody? A couple people? All right, so LDL takes cholesterol from liver to cells. Oops. All right, so if LDL is responsible for removing cholesterol from our liver to our cells, what happens if we have a lot of LDL? Yeah, your cells will take up all the cholesterol they possibly can take, and then you've got this extra cholesterol floating around in your blood. That cholesterol coats your arteries, right? That's why LDL is typically considered bad cholesterol. So if you go to the doctor's office and you get a blood test, they'll give you your LDL and HDL levels. If your LDL levels are high, oftentimes they'll ask you to take a drug in order to get those LDL levels down. HDL is actually different. In this case, it moves cholesterol to the liver. Yep. So in this case, HDL can actually be considered good cholesterol. And oftentimes there is this misconception that any cholesterol is bad and that we need to avoid all cholesterol. They've found out that that's not the case. So have you guys heard about the egg debate? Nutritionists for a long time said eggs are bad. Eggs have a lot of cholesterol in them. You shouldn't eat eggs. And then we realized lately it's not the bad cholesterol. It's actually fine to eat lots of eggs. In fact, eggs are an excellent source of protein. And so they found that dietary cholesterol, especially in the forms of eggs, isn't that bad for you. But what we do need to pay attention to is this LDL level in your blood. If that becomes too high, that's when your increased risk of coronary artery disease goes up. What's that?
I just said thank you.
Yeah. All right, so now let's go to prostaglandins. We've got about 5 more minutes left. So on the bottom of the screen, I've got a list of the different classes of prostaglandins. Like we said, they have 20 carbon atoms plus 5-membered ring plus 2 side chains. Where do you think prostaglandins were originally isolated from? Prostate. Yeah, from the prostate. The ironic thing is that prostaglandins are everywhere in your body, not just in your reproductive system. So it's found all over your body, and they are powerful biological regulators. So they don't just deal with the prostate. They're found in women too. The first one is that they regulate blood pressure. So if you need to vasodilate or vasoconstrict your blood vessels, your body will actually start producing prostaglandins in order to send that signal through your body. These are very important. Next one is blood clotting. So this is a very, very important one. Some people have a deficiency and they can actually bleed out really easily. So like hemophilia patients have diseases that affect blood clotting and they actually have to be given prostaglandins and things like that.
These make up platelets?
No, they're just a biological signaling agent. The next one is that they regulate inflammation. Oops. So if you have an immune response, your body will start producing prostaglandins, tell it to inflame and to keep bacterial cells out. They're also involved in kidney function. And they're involved in reproductive systems. In fact, you can even use prostaglandin to induce labor in women that aren't delivering on time. You can give them a small amount and it'll tell their body, baby's got to get out of you, so do your thing.
That's what they use?
Sometimes, yeah. You have to be careful with it, though, because if you have too high of a dose, it'll actually terminate a pregnancy. So it's a fine, delicate balance that you have to use when you're using these drugs. These are incredibly powerful biological agents. All right. So now let's go to terpenes. So we've got this isoprene unit right here. And so if we count the number of carbons in our isoprene unit, we've got 5 of them. So terpenes have carbons that are multiples of 5. And specifically, they don't have to have double bonds in them, but they do have to have a branch in them. So in this case, it must have a branch. So let's take a look at some example terpenes. And they've circled the terpene units for us right here, but I'll blow it up for us. You can see clearly in this one, it doesn't matter. Don't focus on the double bonds, but we've got 1, 2, 3, 4, and then a branch coming off. That's the 5th carbon. We've got 1, 2, 3, 4, a branch coming off. So that's 5 carbons. If we look at these other ones, they're all multiples of 5. So in this case, we've got 10 carbon atoms. 1, 2, 3, 4, a branch. That's our 5th one. We've got 1, 2, 3, 4, a branch coming off of there. These are all considered terpenes. It doesn't matter if they have double bonds. In fact, they can even be functionalized. So here's some functionalized terpenes where, again, we've got multiples of 5 coming off of them. Let me slide these down. So if we look at menthol, we can actually do the same thing that they've done up here. So we've got 1, 2, 3, 4. So that could be 1 unit. Then we could do the next one. That would be our other terpene unit. So you can go through and identify all the terpene units in these, but they always have these multiples of 5 coming off of them. These are really commonly found in plants, and they're big targets for drugs. So a lot of natural product chemistry focuses on terpenes and their derivatives. So you can see we've got the R-carvone, that's the flavor in spearmint, and then we've got camphor, which is in evergreen trees, so if you rub those needles, you can actually smell them. The other one, too, is that you can have these really, really long terpene units, and we've seen this in our lab. So lycopene and beta-carotene, these are plant pigments. So they've got these long alternating double single bond motifs in them, but essentially they're just terpene derivatives, and they're all different by 5 carbons. So you can have longer and longer terpene derivatives of beta-carotene, for example. All right, so that's our crash course in lipids. Hopefully if you take biochemistry now, this won't look super foreign to you. Yep.
Do most terpenes give off like really fragrant smells?
Some of them do. Obviously, like beta-carotene doesn't. It's too big. It's not volatile enough. Yeah. All right, so tomorrow we'll do exam review. I would recommend taking a look at the practice exam. Come ready with questions, and then we'll go over them.